I'm going to be posting this video to Canvas later tonight as a YouTube link. And you see the count already occurring down at the bottom of the screen there. In the YouTube video, I don't think you'll be able to see the count. All right. Chapter 1. Chapter 1 is starting with this whole scale of the universe stuff. So having an idea of exactly the order of things, and there was this weird pre-SAT assignment that I did like 30 years ago or something, I don't know, 20-ish years ago. And it was just about this girl that got a letter where her address was written way too precisely. So it was her home address, her name, her home address, the state she was in, the country, North America, on Earth, in the inner planets, in the solar system. Okay. In an arm of the Milky Way, an outer arm of the Milky Way. Good. Capital on the Milky Way. Okay, which is part of the local group. Which is part of the Virgo supercluster. Which is part of the Laniakea structure. Which is part of the observable universe. Within the universe, which might even be part of a multiverse. The multiverse part is speculation. Okay. But do be aware of that sequence. Do be aware of the scale of just how big the universe is. And that what we've really focused on is this part right here. I've done a little bit of stuff about what's going on with stars in other areas, but if you are interested in learning about all of this stuff as well, we've got some up division astronomy classes that do cover that stuff. Okay. When we talk about how far away some of these things are, we talk about how far away they are in either light years, or we might even do distances in terms of parsecs or astronomical units. Why would you use these? Okay. Parsec is a unit that we didn't talk about much. It's many light years. Okay, so we didn't really talk about that because most of the stuff we talked about was stuff in our solar system. Okay. Light years, on the other hand, is a measure of how far light travels in a year. Okay. And there's some variations on that as well. For example, there's a light second as well. Okay, so that's how far light travels in a second, which is approximately the distance from the Earth to the Moon. Okay. There's also a light 8 minutes. And the only reason I even use that as a thing is because the sun is approximately 8 light minutes away from Earth. Okay. It takes light 8 minutes to go from the sun to the Earth. In this way, when we look at light, we're looking what happened in the past. Okay? When we see something, it could be a negligibly small amount of time, like from me to you is just a few nanoseconds. So light nanoseconds from each other. Really small distances. Light seconds for stuff to the moon, minutes for stuff inside the solar system, years for measurements to nearby stars. The next closest star is 4.2 light years away. So the light that we see now from that star was emitted 4.2 years ago. And that's how what we see is, it took time for it to get here. Therefore, we're looking into the past. Astronomical units. An astronomical unit is the distance from the Earth to the Sun. Okay, that's 1 AU. It's really good for measuring distances in the solar system, for mostly because it is a distance in the solar system, and you get very easy multiples of it when you measure the distances to the different planets. Okay, so that's what that is. Okay. When we think about light again, because basically this entire course has been a little bit of physics with chapter 3, and mostly the rest has been talking about light in some way. The astronomer's toolkit is all about light. Okay. And we got multiple types of light. We have different ways of observing light. And we use the entire electromagnetic spectrum in our toolkit. Radio waves, microwave, infrared, the visible spectrum, the ultraviolet spectrum, the X-ray, and the gamma. Okay. This was from low energy to high energy, from low frequency to high frequency, from long wavelength to short wavelength. And that's a lot of different types of light. The only part of this that we can see with our eyes is the visible. Now, we can observe radio waves with, radios. We can observe microwaves with satellite dishes. We can observe infrared by feeling the heat on our skin. The atoms within our cells can absorb ultraviolet light. Our skin, our flesh, is not very good at absorbing X-rays, but our bones are. And gamma rays, that's the highest energy stuff. That's stuff that we that can cause problems with our DNA sometimes. What we see is the visible spectrum, all the way from the red to the orange to the yellow, green, blue, indigo, violet. Note that the red is by the infrared and the violet is by the ultraviolet. That's our visible spectrum, sometimes called a Roy G. Biv. What do we do with that light? Well, we observe it, and it's a really big part of the measurements that we do when we do tests. Okay? We do measurements, we do tests, we make hypotheses whenever we use the scientific method. Okay. Where we have some sort of observation or idea. And from that idea, we say, with this in mind, I think that something will happen. We have some sort of hypothesis, some sort of prediction. Okay. So what do we do with this observation, with this hypothesis or prediction? Well, we test the prediction. We test the hypothesis. To do so, we have to run a test. It could be a whole bunch of things. It could be something that's automatically going to happen. We just have to wait for it to occur. It could be something that we actively put into place. But some sort of test needs to be run to see if what we expect to happen actually happens or not. If our hypothesis fails, if our failed hypothesis, well, then we go back to the drawing board. We go, there was something wrong with that idea. Either it was wrong for the situation or it was just straight up wrong. We go back and we review our hypothesis. Maybe we change our hypothesis, maybe we change our situation, and we see if we can make it better. If it succeeds, we double check it. Okay. Was it a fluke? Did it actually happen because of what we expected to happen, or did we just have a serendipitous situation where it just was a confluence of events that made it work? So we give it repeatability, and we do that over and over and over. Okay? And after it's been tested over and over and over, when something is backed by a whole bunch of data, if we've repeated this over and over and over again with lots and lots of blue results, now we got a theory. Okay? Where a theory is an idea that is backed by a lot of data. It's not necessarily law, but it is backed by a lot of data. So we can be sure that it is true in many, many situations. Okay? It's much more than idea. A theory is much, much more than an idea. As you can see, they're on completely opposite sides of the process. Idea, maybe you just saw something happen once. A theory is backed by a lot. There's this weird term mentioned in the book as well. The idea that something could be falsified or falsifiable. Falsifiable? Yeah, if. Okay. What does that mean? Okay. That means that in your experiment, your experiment actually checks whether it's true or false. Checks if your hypothesis is true or false. Okay? Because sometimes people think of an experiment and say, we did an experiment, we didn't get our result. Maybe if we ran it again, it will give us a result. If that's what you're saying after you've done your experiment, then you didn't have a falsifiable experiment. That meant that even when you didn't get a success, it was still open-ended. Okay? That's what falsifiable is actually about. After you do your experiment, it's going to be one or the other, true or false, definitively. Okay? Another way of saying falsifiable is you are checking to see if it is false. Okay. Cool. We got some Occam's razor stuff in there. Just keep it simple. The simplest idea is the most likely the truest one, which is many times true, but sometimes things are complicated as well. It's a little hand wavy on that one. Patterns. Okay. There's a whole bunch of patterns that we look for in astronomy. We've got our patterns that occur on the daily patterns. We have patterns that occur monthly or monthly. We have patterns that occur annually. And we have patterns that occur at times greater than a year. Long-term patterns. Okay. Why do these patterns exist? Well, we got a daily pattern because we have days. We have daily patterns because the Earth spins. We have monthly patterns. We have monthly patterns because of the phases of the moon. Okay. We have annual patterns because of the orbit of the Earth. And we have a bunch of weird long-term patterns. Like we have certain comets that come around. Like Halley's Comet coming by every 75 years or so. We have long-term patterns such as in the solar, in our sunspots. Okay. Where we've got this 22-year pattern of sunspots occurring in high parts of the sun, then low parts of the sun, high parts of the sun, low parts of the sun. We got long-term patterns such as the precession of the Earth, okay, which occurs over the course of over 10,000 years. Okay. We've got a lot of patterns. Okay. Within the annual patterns, we also have seasons. And we wouldn't have those seasons if it wasn't for the tilt of the Earth. Okay. Other patterns. Okay. Other patterns we see, now looking at chapter 2, on different times of the year, we see different constellations in the sky. Okay, and this is approximately monthly as well. We get approximately a different constellation in the sky every, or at the center of the sky every month or so. But in reality, it's more of an annual pattern because it repeats every year. Okay, so there are 88 constellations in the sky. We can't see all of them. We can't see all 88 of them for two reasons. One, because, well, they're on the other side of the Earth from us right now. And to that you might say, oh, well, we'll just wait until they're on the other side of the Earth. 12 hours later, we should be able to see them. And then there's the other issue. Some constellations are only visible from the southern hemisphere, such as we never see the Southern Cross from the northern hemisphere. That is that's the constellation at the very south, very similar to the North Pole here. There they have the Southern Cross. Okay, so 88 constellations is the entire sky. And to clarify, the constellation is an area of the sky. Okay? The stick figure that we see, or the whatever pattern we see in the dots, the pattern is the asterism. Pattern of dots. But there are 12 constellations that get special recognition. Technically 13, but not that much. It's mainly these 12. 13th kind of just dips into there a little bit. There's 12 constellations that the sun passes in front of during the course of a year. Okay? That's along the ecliptic, comma, the sun passes in front of the constellations of the zodiac. Okay. And for that, you've got your Virgos, your Scorpios, your Leos, your Cancers, your Pisces, what am I missing? Aries, Sagittarius, Taurus, Aries, Capricorn, Gemini. Gemini you should say twice because it's the twins. I think that's all of them. And what's the weird 13th one? There's a weird 13th one that just kind of dips into the ecliptic a little bit. I don't know either. It's fine. All right. That's a lot of stuff to keep track of. Okay? So many times we need to think about where things are on the celestial sphere. Okay? Okay. And for the celestial sphere, that's looking at a region around the Earth. So not just what we see in the sky, but the entire sphere around the Earth. Okay. We have our personal dome that we can see at any instant, but the celestial sphere is the entire thing. Okay. What's on the celestial sphere? Well, the celestial sphere does have an equator. Okay. The equator you can think of as an extension from the Earth's equator straight outwards. In the same way as the Saturn has its rings, you can just go straight outwards from the Earth, and that's the equator. The ecliptic is off the equator by 23.5 degrees. Okay. And the reason for that is because the tilt of the Earth is 23.5 degrees off from how it goes around the sun. Okay? That's why we have seasons. Because of how that's tilted. It also means that some days are going to be shorter, some days are going to be longer. Some nights are going to be shorter, some nights are going to be longer. It also means that at night, some nights you'll be able to see a lot of stars in the sky, other nights you won't. There are very few places on Earth where you get to see every single star in the sky over the course of a year. Okay? And that's the places that are near the equator. Near the equator, you can, over the course of a year, see every single star in the sky. But if you live above the tropics, so you got your equator, and then 23.5 degrees above that and below that, define the tropics. One's the Tropic of Cancer, one's the Tropic of Capricorn, because of Tropic of Cancer is when the sun is above that point in the sky. So that's in the middle of our summer. Tropic of Capricorn, which we just passed, which are coming up soon to, at the end of this month. That's when the sun is directly above that point in the sky. We're in San Jose, though. We're over in San Jose. We're at a latitude of 30-ish degrees. So we are. There are stars that we will never see in the sky, and it's basically all the stars that are associated with the southern hemisphere. But we do get to see really cool northern hemisphere stars like everything in Orion. Okay. The flip side of that is that in Argentina, in Australia, in South Africa, in Antarctica, there are stars that they will never see either, unless they travel. They will never see Polaris. Maybe they'll see it in a picture, but they'll never be able to look up at the sky and see Polaris, the North Star. Okay. Yeah. When I went to Argentina, it was weird. It was weird looking up at the stars and seeing something new that I'd never seen there before. I found it really disorienting because I couldn't figure out what direction north was just by looking at the sky. I'm used to seeing the Big Dipper. Big Dipper, that means that's north. But I couldn't because you can't see the Big Dipper from Argentina. Other things to know about the celestial sphere. You've got the northern celestial pole, and you've got the southern celestial pole. Okay. From your own reference frame, okay, in your own sky dome, okay. In your own sky dome, there's limited things you can see at a time because you're only seeing that part of the sky. Things to note about your personal looking up in the sky. You should be able to note where's north, where's south. Okay? You should be able to note where's the east, where's the west. For example, east is where the sun rises, and it's also where all the stars rise and all the planets rise. West is where they all set. The north, if you look at the sun at noon, it will be along your meridian line. The meridian line points from very south to very north and splits your sky in two into your east and west. At noon, the sun is as high as it gets in the sky. But sometimes the sun doesn't get very high in the sky. If you're in the northern hemisphere, like we are, if you're north of the tropics, the sun will never get to your zenith. The zenith is the point straight overhead. You should know the zenith. Opposite of the zenith, if you point down straight through the earth, that's your nadir. Okay? Okay. So, at our location, the sun does get high in the sky, but it never gets to your zenith. If you live in the tropics, then it goes back and forth across your zenith over the course of the year. And if you are in the southern hemisphere south of the tropics, then the sun will never be at your zenith either. But when you are in the very north or the very south, what you do get are circumpolar stars. So from our perspective of the northern hemisphere, when we look at the North Star, which is approximately there, then over the course of the night, stars will rise in the east, set in the south, but the ones really close to it will just go in a circle. So over the course of the night, there are some stars that never rise or set. Those are the circumpolar stars. And there's a really pretty picture of them in the book. There's some distinctions between latitude and longitude. There's some things in here about being able to see the difference between, hey, is this part of the Earth in winter? Is this part of the planet in summer? And goes about accordingly in that nature. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Just the 12. All right. Anything else? There are parts in the Arctic Circle that are at the extreme. In the Arctic Circle is where you can get nights that last more than 24 hours, and where you can get days that last over 24 hours. Okay? During the summer at the North Pole, it just stays bright the entire year. But during the winter, not the entire, for 6 months, but during the winter, it stays dark for 6 months. Now, it's not total darkness. You get this weird, hazy look, similar to twilight, when the sun is just below the horizon. So you get this weird glow in the distance. So it's a really eerie kind of darkness. You can get a hint of it if you go to Alaska for any sort of purpose, really. We have our solstices. We have our equinoxes. Okay, We had our autumnal equinox during our semester. That was the September, I think it was the 22nd this year. But it's usually September 20, 21st, 22nd, something like that. That's the autumnal equinox, where it's half day, half night, 12 hours of each. As you were able to tell recently, the days are getting shorter. So the autumnal equinox is half day, half night. That's what's equal about it, is it's half day and half night. We are heading really close to the winter solstice, which is December 20-something. And that is your shortest day of the year and your longest night. And apparently, it's a miracle if you can get oils to last extra long during that time of year. Hence why we have Hanukkah and stuff like that. Because during the longest nights of the year, that's when you need the oil to light your lamps, or electricity nowadays. Then we go into the new year. In the new year, a few months later in March, we get to the spring equinox. March? April. I forgot when the spring equinox is. But again, that's a half day and half night deal. Okay? Until we get to the summer solstice, where that is your shortest night and your longest day. Okay. Great time to have a barbecue during the day, and just because you get to stay awake for a long time and it's still day. All right. Tropics, vernal equinox, Gregorian calendar, Arctic Circle, precession. Precession. The precession is the wobble of the axis the Earth spins along. Spins around. Period. But it's not something that we observe in our lifetimes. Okay, this is something that takes thousands of years to occur. Okay, it takes 26,000 years for the precession to complete a single rotation. What this means is the thing we call the North Star isn't always the North Star. The fact that we have a star that is right next to, right along our axis right now, is just a happenstance of the time. Lucky for us type of thing. There were thousands of years where there was no North Star. We just had, that constellation there is near the North Star, which would be the Ursa Minor. But other times it was Draco, other times it was Cygnus, other times it was Cepheus, Vega, and a few others. So, cool. Another pattern Another pattern we have is the phases of the moon. And we have phases of the moon because the moon does a synchronous rotation. Which is that it's the part of the moon that we see is always the side that's pointed towards us. And that's just the way that its orbit wound up. It is a common way for orbits to end up, but it's the way it just happened to end up for ours. So the same side of the Earth always looks towards us with only a tiny wobble. But it's not always illuminated. Because it's not always illuminated, we have different phases of the moon. Starting with a new moon, where we just don't see it because it's backlit. Then a waxing crescent. That's when it looks like this little sliver. Then we have our first quarter. Okay. Not first half. First quarter moon. So the crescent, it's all dark except for just a little sliver. For the first quarter, we can see the right half of the moon. Then we have our waxing gibbous. And that is where we can see kind of a full football of the moon. Full moon. Rather self-explanatory, I think. We see the whole face. Then things start going the other way. Instead of waxing, it's waning. So we got a waning gibbous. Then we've got a third quarter moon, where we only see the left side. We've got a waning crescent. And then repeat. That's approximately a month, about 29 days. Okay. Sometimes you can get eclipses as well. Okay. There are solar eclipses and there are lunar eclipses. Okay. If you can see the moon, if it's a full moon time of year, that means that it's possible to have a lunar eclipse. Did anybody see the lunar eclipse? I think it was last week or the week before. Yeah? Yeah, there was only one person in the other section that saw it. I was like, okay. I think a lot of people are just like, nope, I was studying. It's either I'm working, I'm studying, I'm going to class. If I'm not doing that, I'm sleeping. It's about right. During a new moon, that's when it's possible to have a solar eclipse. And that's the one where if you ever have the opportunity to see a solar eclipse, do it. It's worth traveling to see. Sometimes solar eclipse. Why not always? Why not always is because there's a 5-degree difference between the plane of the Earth. There's a plane of the moon's orbit, and the plane of the Earth's orbit. Okay, so they're just 5 degrees off from each other. For that reason, they just don't always line up. So you only get them to line up at ascending or descending nodes. Not a term I'm really wanting you guys to know. Okay. There we go. During these eclipses, sometimes you can see them for over large areas. Sometimes you can only see them over small strips of the Earth. Okay. The lunar eclipse, as we saw recently, was visible to half the world. Okay. Half the world was able to look up in the sky and see the moon was red, assuming that they didn't have clouds in the way, or they were outdoors. So, but everyone on that side of the Earth that was outdoors on a clear day, or clear night rather, was able to see it. Okay. That is not the case for solar eclipses. For solar eclipses, they're only visible over a small track of the Earth. Okay. During these eclipses, there are different types of eclipses within those. There are partials, there are totals, and there are annular eclipses. Okay. The partial eclipses just means that it didn't fully cover it. Okay. Where maybe a little bit of the umbra and penumbra went across the moon, but not the whole thing. Okay. For total, that means the thing was completely blocked out. Okay. Annular is similar to a total. Annular is similar to a total, except during some solar eclipses, you see the sun behind the moon still. This happens when the moon is a little bit further away than normal, because it does go away and come back a little bit. So if the moon is just a little too far away, you get this ring of sun around the moon during a solar eclipse, and that's called an annular solar eclipse. It's doing its best to cover the sun, but it's just too far away to cover it the way you'd expect it to. That's chapter 2. Chapter 3. Chapter 3 is practically a physics chapter. Okay? It's about the laws of motion. Okay? It's a consideration of what we see in the sky, why we see things in the sky, and what's going on. And it always starts with history. It always talks about the Greeks looking the patterns in the sky and them saying, everything's going around the Earth. So there must be a geocentric universe. But we have a few weird things. We have these wanderers. We have these planets. Sometimes they're not going the same direction as the other stars. Sometimes they're going the wrong way, like we're observing with Venus. Venus is currently in retrograde motion. So it's not going the same direction as all the other stars. Because it's not a star, it's a planet. It's close by and doing a different thing. How did they handle this retrograde motion? Well, they had an idea of circles on circles. Ptolemy had this idea of circles on circles, where he saw the planets going around their orbits, but within that orbit, they also went in a circle. And it just ends up being that you can do that with anything. There's a mathematical theorem that shows that you can draw any shape if you just keep on nesting circles of different size to make it travel weird circles. They also had limited data. They could only use their eyes only. Okay. Because they had their eyes only, they knew about the sun. They knew about the moon. They also knew about Mercury, Venus. Obviously, they knew about Earth, Mars, Jupiter, and Saturn. But they couldn't see Uranus, they couldn't see Neptune, and they had no concept of there being a planet called Pluto out there at all. They also didn't know about asteroids. Sometimes they would see a comet, sometimes they'd see an asteroid skimming through the atmosphere, but this is basically it. And a bunch of stars, the very distant stars. Then, Copernicus, thousands of years later, Copernicus, we're looking at about 600 years ago, Copernicus said, no, these patterns seem to be not the everything going around the Earth. It seems like everything's going around the sun. Copernicus was the first one to publicly say, no, we got a heliocentric solar system. And they were still doing eyes only, and it didn't go over very well. Then Kepler came along. And Kepler was able to borrow a whole bunch of data from Tycho Brahe. And Tycho Brahe slowly doled it out, miserly, throwing parties and whatnot. It's all about him. But Kepler was able to do something with this. And he was able to come up with his Kepler laws for orbits, for 3 laws. One, it's not circles. The orbits of the planets are ellipses, and they are heliocentric. So the sun is at one of the 2 foci of these ellipses. 2, the planets do not always move at the same speed. Okay? When they are close to the sun, they go faster. And then when they're farther from the sun, they go slower. And this variation is very small for the planets. It's very big for the comets. Comets like Halley's Comet stay out there for most of the 75 years, and we only see it close to Earth for maybe 1 of those years. And for most of that year, you need a telescope to see it. Okay. This is also called the equal area and equal time. And there's a nice drawing for that in the book that you can take a look at. Third rule, okay? Third rule is comparing different orbits. So, and it's one of the few equations that we have for the semester. And that is the period squared is equal to the distance cubed. Okay? And this has to be done in units of years and AU. So years for the period and AU, astronomical units for the distance. What does this mean? That means that a planet close to the sun, like Mercury, is going to have a very small period. Whereas something far from the sun, like Pluto, is going to have a very large period. So much so that Pluto hasn't even completed an orbit since it was discovered. Okay? Didn't even get it to take an entire lap. No victory lap, no nothing, just cut short. And that's okay. And something about these laws that he came up with. They're very observation and math centric. He's a very good mathematician, very good at following the data where it leads. And he didn't know why it had to be ellipses. He didn't know why equal area and equal time had to occur. And he didn't know why the period squared had to be equal to the distance cubed. But he knew that the math worked out. Okay? So he just was able to observe that this is what was happening. Then came Galileo. Galileo is finally telescopes. Okay? No more naked eye astronomers. Galileo was able to look through telescopes. He was able to figure out some basic laws of motion. But he was mostly known for his observations with telescopes that really cemented the idea of a heliocentric solar system. For one, he saw the moons of Jupiter. Which meant that no longer were things just going around maybe the Earth and maybe the sun. There were things going around a whole nother planet that people could barely see. So it's not special that our moon goes around the Earth. Moons go around other planets as well. 2. He was able to see the structure of the moon. He was able to look at the moon and say, that is not a perfect sphere. That those splotches on it are actually things of different elevations. There's different crags on different parts of it. So the moon is not a perfect sphere, so we should not be expecting just circles and spheres everywhere. It should be variations on ellipses and different squashes of things similar to spheres. Oblate spheroids and the like. 3rd, he was able to observe the phases of Venus. And this is the really big one that really says, oh no, Venus is sometimes on the far side of the sun and is sometimes on the close side of the sun and is going back and forth around the sun. And we can see that based off of the type of phases it has. When it's a full Venus, we see a full Venus when it's in the same part of the sky as the sun, on the far side of the sun. Venus is never on the opposite side of the Earth from the sun. So you never get a sorry, you never get a full Venus over there. It's always next to the sun. So it must be going from the opposite side of the sun to the close side of the sun, back and forth. Okay. Then Newton came along. And Newton, guy knew how to take advantage of a pandemic. He wasn't able to work with everyone else, so he studies his own stuff and figured things out for himself. And he was able to come up with 3 laws of motion, and a universal law of gravity. Which is mostly correct. All right? The 3 laws of motion. The first law of motion is the law of inertia, where he was able to observe that an object in motion will remain in said motion until acted upon by an external force. And this is very similar to something that Galileo was saying as well. Okay? It's almost a rewording of what Galileo was able to do. Because Galileo worked with the idea of velocity and acceleration. And Newton was able to expound on that. 2, another equation. F equals ma. Which tells us that it takes a force to make a mass accelerate. Now, if it's a big mass, it's harder to accelerate. If it's a small mass, it's easier to accelerate. If you apply a little force, it's not going to accelerate very much. Okay? And he was able to apply these in linear motion and in circular motion too. Okay? His third law of motion is the action-coaction pair. Now, every other book out there is going to say action-reaction pair, but it's not a reaction, it's happening at the same time. It's a coaction. So that action-coaction pair says that as one thing is pushing a second thing, the second thing is pushing right back. As I press my hand onto the table is pressing right back up on my hand. This is why you can gently hit a surface and it will gently hit you back. Or you could pound your fist on something and it'll pound your fist right back and hurt your hand. Okay. That's the action-coaction, or also called the action-reaction pair. It's also called a third law pairs. And then, and then we get to the universal law of gravity, which is saying that in order for things to gravitationally interact, there has to be 2 masses, and when they're close, it's going to be a strong force. When they're far away, it's going to be a weak force, and it's always attractive. Okay. We're at 1 minute to go. No longer a minute to go. And I didn't say anything about, I'm just going to mention it as we're going out the door. There's a difference between a circular orbit, an elliptical orbit, a parabolic orbit, and a hyperbolic orbit. Okay, these are the bound orbits. They actually repeat over and over, and the parabolic and hyperbolic are unbound. That's stuff that's going around the Earth but never coming back again. That's it. I'm going to save this, post it to YouTube tonight, and then later tonight it'll be available on Canvas. All right. See you guys Thursday.
Thank you, Professor.